beginning now and for the rest of the course, we're going to talk about my favorite area of chemistry, and that is quantum mechanics and those parts of chemistry that are governed by or explained by quantum mechanics. So Chapter 5, your book calls Periodicity and the Electronic Structure of Atoms, and that is because we need quantum mechanics to explain the periodic table and the way that electrons and atoms behave. Chapters 6 through 8 are going to deal with bonding and how molecules and compounds and ions are formed, and all of that is governed by the behavior of electrons, which is governed and explained by the principles in quantum mechanics. So that's really what we're going to be talking about for the rest of this course. To give us a little bit of an intro on that, we'll take a look at one of the periodic trends that we notice. We look at the periodic table and we put all of the elements, we make a plot of atomic number, which is number of protons in a nucleus, versus how wide the atom is, atomic radius. And we notice that we see this repeating trend of going to a peak and then going down, peak, and then down, peak, and then down. We flatten out a little bit, peak, down, flatten out, peak. Notice that all of these peaks, all of these high points, these maxima on the graph, are elements that are in the first column of the periodic table. And these minima are elements that are in the fluorine column of the periodic table. This particular chart ignores the noble gases, but the periodic table was around for several decades before the discovery of quantum mechanics. And the way that the periodic table came into being was that Dmitri Mendeleev, a famous scientist, decided to try to make a chart of the elements, or table of the elements, that placed all of the elements that were similar to one another chemically in the same column as one another, but still kept them in order by their atomic mass. Now, that was because back then we didn't know about protons, we didn't know about atomic number, and so the table became easier to put together once protons were discovered, which again was still before quantum mechanics. And so, as it turns out, these are all experimental observances, experimental things that we can see and observations we can make. But in order to explain why atoms behave this way, we'll need quantum mechanics. And so that's what we're going to spend some time talking about. Before we get into that, we can talk about some of the other experimental discoveries that led to quantum mechanics. And we'll begin with talking about what light is. When we talk about light that we can see, we're talking about electromagnetic waves, alternating electric and magnetic fields, where the waves each have a length of somewhere between 380 nanometers, 3.8 times 10 to minus 7 meters, and 780 nanometers, 7.8 times 10 to the minus 7. Light that has longer wavelength than that, or lower energy or lower frequency, and we'll talk about frequency on the next slide, is what we call infrared light. We can't see it, but it does come from objects that are hot. There's infrared light coming from the sun. There's infrared light coming from a hot stove. The hotter something is, the more infrared light it gives off, until it gets to the point where it's hot enough to glow red or glow at some visible color. Even lower energy, lower frequency, but longer wavelength waves are microwaves, and then radio waves. And the length of a wave is smaller than really we can see with our eyes for visible light, about the size of a bacteria cell. But for infrared light, the size of a dust particle would be the length of a wave. And we get up to a pinhead for microwaves, and then really macroscopic objects, humans are bigger, for radio waves. Smaller waves than we can see would be higher energy, ultraviolet, the size of a virus capsid, or X-rays around the size of an atom, or gamma rays even smaller and tighter. Now on this axis we show the frequency. Frequency is defined as the number of wave peaks that pass by a particular point in space in a certain amount of time. So we measure it and say peaks per minute, or more often peaks or waves per second, And so that per second unit for waves frequency is called hertz. The length of a wave, what we're calling a wavelength, is the distance from one peak of a wave to the very next peak. And the amplitude is the height of the wave. And we get, for example, in light, the more intense a beam of light is, the brighter it is, the larger the wave's amplitudes are. And we'll work some problems to illustrate this in class when we meet. Out of all of that light that I mentioned as visible light, I never mentioned white. A lot of the light that we see that comes from incandescent bulbs or fluorescent bulbs is what we would call white light. And you didn't see that at all in the frequency chart I had up earlier. And that's because light that we see as white light is actually a mixture of all of the colors of visible light. And the way that we can tell that is light all travels at a certain speed when it's going through air or through a particular medium. But when we force it to go through a denser medium like glass, the different frequencies of light travel at a different speed. And so if we force them through a triangular shaped piece of glass, that'll cause bending of the light, and certain wavelengths will be bent further than others, and that white light can be spread out into what we call the rainbow. One of the things that scientists notice, and we're going to take a look at this in class and in lab, is that when we excite certain atoms, they tend to glow at specific colors. For example, if we shine white light through a prism, then this entire area would be covered with light. We'd see all the colors of light. But if we take light from a sodium lamp and shine it through a prism, we get these two lines both in the yellow area. If we take light from a lamp that has hydrogen gas in it, and the light's generated by pumping electricity through that hydrogen gas, and we take that light and shine it through a prism and detect what colors of light come out, we notice that we only get these four stripes: a blue, a couple kind of bluish green, and then red. And so we call these atomic line spectra, the kinds of lights generated by exciting, usually electronically or with heat, exciting specific elements. And the first equation to come out to try to explain that is the Balmer-Rydberg equation. And we have it written out here, and we talk about electronic excitations. This was in the 1880s. 1 over the wavelength of the light that we see is equal to this constant we call the Rydberg constant times 1 over a particular integer squared minus 1 over some other integer squared, and we get the exact wavelengths we see for the hydrogen spectrum by using that equation. So the m and n are whole numbers that are both where n is a larger number than m, and like I said, that r is a Rydberg constant, and depending on our units we'd have different numbers here, but if we want our wavelength to come out in nanometers, we'd use 1.097 times 10 to the minus 2. And the other relationship that we want to look at and use, it was discovered primarily by Max Planck in the late 1800s, is that the energy of a particular light isn't related to how bright it is. It's related to its frequency or its wavelength. So H is called Planck's constant. So you don't have to memorize the number, but it's 6.626 times 10 to the minus 34. C is the speed of light. Approximately 3 times 10 to the 8th meters per second, 300 million meters per second. And lambda is the wavelength of a particular wave. And so the brighter a light is, the more intense it is, the more of that particular energy that's coming across. But each piece of light, and we're going to have to describe that in a little bit more detail later on, each piece of light has an energy that's associated with its wavelength in this way. And we'll take a look at some examples of using this using both of these equations in class when we meet. In 1905, this actually became Albert Einstein's Nobel Prize discovery. A lot of people think he got the Nobel Prize for his discoveries related to theory of relativity, and that's not the case. He got his Nobel Prize for his discoveries related to the photoelectric effect. What he noticed is that if you take a piece of metal and shine light on it, if the light is of high enough frequency, of high enough energy, or small enough wavelength, it will eject electrons from the metal. And if we take a light that is a little bit lower than that threshold, then that amount that is necessary to cause electron ejection, the ejection will not happen no matter how bright we make that light. But as soon as the light gets to the color or the wavelength, the frequency that's necessary to cause ejections, the ejections happen. No matter how bright the light is, they just happen more often, more electrons per second ejected, the brighter or more intense the light beam is. This led to Einstein coming up with this idea that light isn't really, or can't all the time be considered waves, but that we should consider light to be little pieces of energy. He called those photons, little particles that travel on a particular wave, and the energy of that particle, the energy per particle, is what's related to the wavelength or the frequency by Planck's equation. Louis de Broglie in 1924 built on Max Planck's work a little bit, and on Einstein's relativity work, and worked out this equation for the wavelength of a particle that's not light. So if we assume Planck is true, then we solve for wavelength, and we know E equals mc squared, and we substitute that in, mc squared in for E, and we'll notice C divided by C, we'll cancel out one of those C's. We get the wavelength of light, for example, is